Hello to my physics students. Yes, this is Miss Nevin. Hope everything's good with you guys. Hope that you are healthy and well rested and ready to learn some physics. So, the next unit that we were going to start on Monday, but I guess we'll start it now, is electric current. You guys know all about electric charge now. So now we're going to talk about what happens when those charges move around. So current is the flow of electric charge through a substance. And we know that the electric charges that are moving are really the electrons in the atoms. But we're not going to define current as specifically the flow of electrons. We're going to define current as the flow of electric charge. And you'll see why in a second. See if you can think of some other things that flow. So one idea of something else that flows is water. And when you see water flowing in nature, it usually flows from high to low elevation. Another thing that flows is air. And air flows usually from high to low pressure. When this happens on a large scale, we call it wind. Or you can picture squeezing a balloon and the air flowing out of that high pressure balloon into the relatively low pressure room. So, electric current flows from high to low potential. And potential, you might remember, is one of those weird things on the right side of the magic square. Potential is potential energy per charge and is measured in volts. So high to low potential. If I have a positive charge over here and a negative charge over here, and I've got these points A, B, C. Think about the amount of potential energy that a small positive charge would have at each of these 3 points, and decide which point is going to have the highest potential. Yeah, it's going to have the highest potential at point A because that's the place where it's kind of the most difficult, takes the most work to put a positive charge here at A. And it's the easiest, it takes the least amount of work to put a positive charge here at C, so that has a low potential. So a positive charge would flow in this direction. Hang on a second, you might say, but the things that are moving are actually electrons. Those are negative charges, so they want to flow in this direction, from low to high potential. That's confusing. And this is what we call conventional current. Is the movement of positive charges. It turns out that this is equivalent to electrons. This E minus is the abbreviation for electrons moving in the opposite direction. So if I have a conductor here, it's got positive nuclei in the atoms, and we've got electrons moving through this conductor. Say the electrons are moving to the left. So at first, maybe I have an electron here and an electron here. So overall, I'm kind of neutral here, positively charged here, and neutral here. If this electron moves from here to here, now, remember at first I was sort of positively charged here in the middle. After this electron moved over, I'm positively charged on this end to the right. So electrons moved to the left, conventional current moved to the right. This is equivalent to saying that the positively charged area in the middle here moved to the right over here, because now we're neutral in the middle and positively charged over here. And really, every part of the conductor is usually pretty close to neutral because the positive and negative charges are equally distributed. But the physics that we see as a result of negative charges moving to the left is the exact same physics, the exact same changes in energy, the exact same changes in fields, things like that, as we would get if there was positive charges literally moving to the right. When they were first doing experiments with current, they didn't know what type of charges were moving in which direction, but they could observe the effects of current flowing. And so they labeled a certain direction as being positive current, basically, and it turned out that that's not the type of charge that actually moves, but we still say that that is the direction of conventional current. So even though technically it's really electrons going in the opposite direction, we say that current flows from high to low potential, and you can essentially pretend that there are a bunch of little positive charges moving through whatever is having current flow through it, even though really it's electrons. From this point on, in this unit and in circuits as well, we are basically going to forget that electrons exist and only talk about conventional current. A substance that can carry current is called a conductor. Units for electric charge, you should remember, are coulombs. And units for electric current are a coulomb per second, or this unit has a special name, amps or amperes, named after a scientist who was discovering this kind of stuff. And we use the symbol I for current in formulas. So on the reference table, the next equation in the electricity section that we haven't covered yet is this formula, I equals delta Q over T. So I is the current, Q is the charge, and T is the time. And this is the amount of charge that passes a point in a second. So if we were still thinking about electrons, we would count up how many electrons went by during 1 second. Or with conventional current, we're pretending that these are little positive charges. We're counting how many coulombs of positive charge went by in a second. These numbers of charge can be a lot bigger than the charge numbers that we were using in the electrostatics unit, because that charge does not need to be all in one place, and it's not an amount of unbalanced charge. It's basically how many went by in a second. So if we were looking at a wire and we had a bunch of little positive charges flowing to the right, we would basically watch right here and count how many went by. If 3 of these charges went by in 1 second and each one had an elementary charge, then that Q would be whatever the 1.6 is times 3. 4.8 times 10 to the negative 19 coulombs. Electric current is measured with an ammeter. Which measures amps, as you might guess, or amperes. And the circuit diagram symbol is a circle with an A in it. So as I was kind of describing, like sitting at a certain point and counting how many goes by, you can physically connect up a device, an ammeter, and it will count how much charge goes through it every second, and it will tell you the amount of current as a number in amps. Okay. In order for current to flow, there needs to be a connected circuit made of a conductor so there needs to be some place for the charge to go, and there also needs to be a potential difference or voltage is a more casual word for a potential difference. So this is basically what pushes the charges. You could think about the electrostatic force as being what pushes the charges, and in electrostatics, that's how we talked about it. But through the magic square relationships, the potential difference is related to the electrostatic force, and it ends up just being mathematically an easier quantity to use to describe how much the charges are being pushed. Okay, but it's not a literal push, it's not a force, because technically it's related to the force, but through those magic square relationships. Okay, so let's do a little bit of practice with the equations. We've got, we've got in 10 seconds, 2 coulombs of charge flows through a wire. What is the current? So try to use this equation and find the current and include the correct units. Okay. So this 10 seconds is T. This 2 coulombs is Q, or delta Q. And then it wants to find the current, so that is I. So I've got I equals delta Q over T. That's going to be 2 coulombs over 10 seconds, or 0.2 coulombs per second, which is amps. Okay. This delta in the formula really just refers to the fact that we're counting how many passed a certain point, and it's not necessarily adding up all the charges within the entire circuit, but counting during a certain interval how many passed a point. So it's not a separate variable that you need to plug in. Whatever charge you're given is the delta Q. Okay. Now try example 2. Pay close attention to the units that you are given. All right. So 0.1 coulombs of charge flows through a lamp during 1 minute. What is the current? So this 0.1 coulombs is going to be delta Q. 1 minute. Our time is going to be 60 seconds. And then we're again looking for the current. So we have I equals delta Q over T. 0.1 coulombs over 60 seconds equals, I'm going to use my calculator on this one, 0.1 divided by 60 is 0.00166, repeating, I'm just going to round that to 167 amps. It's not that uncommon to have a fairly small number for amps, especially for the types of circuits that are made with a little circuit kit that we use, because they're meant to be pretty safe. And it turns out that a lot of current can be kind of dangerous, so small amounts like this are what you would work with in, say, a lab activity. Okay. You can write out this number in scientific notation if you wanted to. 1, 2, 3. I always move the decimal point to one place after the last digit. This would be 1.67 times 10 to the negative 3 amps. And there's actually a metric prefix for this 10 to the negative 3. And that's M for milli, as in millimeters. So I can write this as 1.67 milliamps. And this is the reading that you would most likely get from an actual ammeter. If it's going to be a small amount of current, then it will report it in smaller units. And this is also the amount that you would see like listed in instructions for something. It would be in the units that make the most sense, because this number 0.00167 is kind of a small number, hard to picture. So it's pretty common to convert into the units where you will get like a number, at least a whole number or more, like more than one. All right, so that's it for the notes on electric current. And I'll have a next video up for you soon on resistance.